myself Dr. BJD Kalyani, working as Associate Professor in the Department of Computer Science and Engineering of Institute of Aeronautical Engineering. In this video, I will discuss about Booth's multiplication algorithm. At the end of this video, the student will gain the knowledge regarding how binary multiplication can be performed, what is the hardware requirement to perform the binary multiplication, and what is the process flow chart for the Booth multiplication algorithm. So the basic agenda of this video is introduction and the examples regarding the binary multiplication, the hardware requirement of the binary multiplication, and the process flow chart for binary multiplication. In previous videos, we discussed about the binary addition and subtraction. But binary multiplication is a bit complement when compared to the binary addition as well as subtraction. So this complex task has to be reduced with the help of some hardware and with process flow charts. So more complex operation can lead to more area and also more time. So normal multiplication algorithm can be occupy more time as well as space and time complexity of that algorithm is more, but Booth's multiplication algorithm can be efficient when compared to the normal binary multiplication algorithm. First, we will look into how to perform the binary multiplication. So, here we considered a multiplicand as the example and one multiplier as the in this example, and how the binary multiplication can be carried out with this multiplicand and multiplier. So first we have to consider the LSB of the multiplier. With this LSB, we have to multiply all the digits of the multiplicand. So if in the binary system only there is two digits, either 0 or 1. In case of 1, the multiplicand can be copied in the partial product. In case of 0, the number of bits that are there in the multiplicand, that many zeros can be copied in the partial product. So here this bit is 1. So the multiplicand can be copied here in the partial product. And whenever after copying this, we can move to the next bit. The next bit is the 0 bit. So 0 means how many number of bits in the multiplicand, that many zeros can be copied in the partial product by leaving one bit space. So here this is the second partial product. Next, consider the next bit 1. So the multiplicand can be copied in the partial product by leaving the one space. Like this, the partial product terms can be identified. At the end, all partial product can be summed in order to get the binary multiplication value. This is the procedure to perform the binary multiplication. So the initial multiplication algorithm that is available require the hardware like the B register, A register, Q register. So Q register has to store the multiplier, B register store the multiplicand, and A register is the accumulator in order to store the partial product terms. So there should be a complementer and parallel adder in order to perform the basic operations while performing the multiplication. And here this is the sequence counter. And in the normal multiplication algorithm, the multiplicand can be stored in B register, multiplier is stored in the Q register. By using the XOR gate, the signs of the two numbers can be either they are same or with different signs. The two numbers involved in the multiplication can be checked with the help of exclusive OR gate. A is initially having the 0 value, E is extra storage bit, and it is a flip-flop and it is initialized with the 0. The sequence counter can be initialized with the number of bits of the multiplier. How many bits there in the queue? That many the number of bits can has to be initialized to the sequence counter. So while performing the multiplication, the LSB of the multiplier can be first considered. So here we considering the LSB of the multiplier. So the Qn is the LSB of the multiplier. Multiplier is stored in the Q register. So here checking whether this value is either 0 or 1. So if it all 0 means simply we have to shift right operation can be performed on the flip-flop E and the register AQ. So shift right operation EAQ can be performed and the sequence counter can be decremented by 1. In case of the Qn value contains the 1, A plus B can be performed. The multiplicand can be added with the A register value, and if it all extra bit generated, that is stored in the E. Later on, the shift right operation can be performed on EAQ and reduce the sequence counter value by 1. So this process has to be repeated until SC can have the sequence counter can have the value 0. So like this, the process steps can be performed in the normal multiplication algorithm, but it occupies more space as well as it requires more time. So the time complexity and space complexity of this normal multiplication algorithm is more. So in order to make this algorithm efficient, the next variant of the multiplication algorithm is the Booth multiplication algorithm. The Booth algorithm is a multiplication algorithm that allows us to multiply two signed binary integers in 2's complement respectively. So here the signs can has to be preserved after the multiplication process, and here 2's complement numbers can be considered. It also used to speed up the performance of multiplication process, so it is very efficient. So here the efficiency can has to be measured with the time and space. Both can has to be optimized in case of Booth multiplication algorithm. It works on the strings of zeros in the multiplier that requires no additional bit, only shift rightmost string bits, a string of ones in multiplier bit. So weights of 2k to weight 2 power m, that can be considered 2k plus 1 is equal to 2 power m. So in order to perform this step, arithmetic shift right operation can has to be implemented in order to gain the maintain the same weight value. Here arithmetic shift right operation can has to be performed in Booth multiplication algorithm. And the hardware requirement for this Booth multiplication algorithm is here register Q is storing the multiplier, multiplicand, and also the partial product can has to be stored in the registers. And here after checking, it is considering the 2 bits of the multiplier and has to check based on these 2 bits of the multiplier. Based on the condition that can match, the action has to be performed. So the process that can be involved in the Booth multiplication algorithm is like this. Multiplier and multiplicand are placed in Q and M registers. So 2 registers are taken. The Q register can has to be stored in the multiplier value and multiplicand value is stored in the M register. So result from this will be stored in the AC and the Q register. Initially AC, Q registers will be AC and Q1 register will be 0. Multiplication of a number is done in a cycle. So a 1 bit register Q1 is placed right of the left significant bit of Q0. Multiplier LSB Q0 the left of it is placed the Q1. Initially, it is having the value 0. So, in each cycle, the Q0 and Q1 bits will be checked. So, 2 bits can be considered for validating the multiplication process. So, here, if Q0 and Q1 are 1, 1 or 0, 0, then bits of AC, Q, Q1 are shifted to the right by 1 bit. If the value is shown in 0, 1, then multiplicand is added to AC. After addition, AC, Q0, Q1 registers are shifted by right by 1 bit. If the value showed is 1, 0, then multiplicand is subtracted from AC. After subtraction, AC, Q0, Q1 registers are shifted by right by 1 bit. So, this is the general procedure that can be followed in the Booth's multiplication algorithm. Now, this procedure has to be explained within a flowchart. So, this is the flowchart of the Booth's multiplication algorithm. So, here the A register can be initialized with the 0 and Q1 is initialized with 0. Multiplicand is stored in the M register. Multiplier is stored in the Q register. And count is how many number of bits are there in the multiplier. Those bits can has to be that number of bits can be as a count can be stored. So here Q1 is initially 0 and Q0 is the LSB of the multiplier. By taking these 2 bits, the validation condition checking can be performed. Whether it contains 0, 1 or 1, 1, 0, 0 or 1, 0. So with the 2 bits, the 4 possible combinations are 0, 0, 0, 1, 1, 0, 1, 1. So with these 2 bits, these 4 combinations are checked. If the 2 bits contains the 0, 1 value, then A value can be added with the multiplicand. Then arithmetic shift right operation can be performed on A, Q0 and Q1 bits. Then the counter can be decremented by 1. In case of these 2 bits contains the value 1, 0, then A minus M operation, the subtraction operation can be performed. Later on, the arithmetic shift right operation can be performed on the A, Q0, Q1 and count can be decremented by 1. In case of these Q0 and Q1 can contains 1, 1 or 0, 0, then directly the arithmetic shift right operation can be performed on A, Q0 and Q1 and count can be decremented by 1. After performing these steps by checking the 2 bits of the LSB of Q0 and also the Q1, then the counter value can be checked. So this process has to be repeated in a loop until the counter value is 0. If counter contains the 0 value, then this process can be ended. So this is the procedure for Booth's multiplication algorithm. Now we have to look into how to perform this procedure by taking one example. So here we taken the example as M is 0, 111 and in order to perform the minus or the subtraction operation, 2's complement addition can be used, which has to be in order to find the binary subtraction. So here the 2's complement of M can be 1, 0, 0, 1. So AC or A register can initially contains the 0 value and this is the Q value multiplier value. Qn plus 1 is 0 initially and Qn is 1. So in order to check the 2 possible conditions 1, 0, if the 2 bits combination consists of 1, 0, then A minus M operation can be performed. Later on, arithmetic shift operation can be applied on A, Q0 and Q1. So here, the subtract operation can be performed with the help of 2's complement addition. Later on, the arithmetic shift right operation can be performed and the counter value can be decremented by 1. So, initially it is 4, now it should be 3. So, next Q0 and Q1 bits can be taken into consideration 1 1. So, if it contains 1 1, these 2-bit combination contains 1 1, then arithmetic shift operation can be performed and counter value can be decremented. So, shifting operation has to be performed and the counter value can be decremented. Next, by taking the 0 1, next 2 bits, if it all the combination contains the 0 1, then the addition, this subtraction operation can be performed. Next, 0 1 combination, if Q0 and Q1 is 0 1, the addition operation can be performed. Then arithmetic shift right operation can be performed. So, let's the Q0 and Q1 bits has to be compared 0 0. Simple arithmetic shift right operation can be performed. So the counter value can be 0. There at this time we have to stop the process and the product can be available in the AAC register and the Q register. So this is the procedure for the both multiplication algorithm. Now we will look into the example. So here we consider the M. So multiplicand can be 0 1 1 and multiplier is 0 0 1 1. So here whenever we are performing the subtraction, we are using the 2's complement addition. So first we have to find the 2's complement of M. So M value is 0 1 1. So 1's complement of M is 1 0 0 and 2's complement of is 1's complement plus 1. So here we have to add a 1 to 1's complement. This is the 2's complement of M, the multiplicand. The multiplier is Q. So Q is 0 0 1 1. Now we have to perform the first step operation. So this is the first step operation, that is the initialization of various registers. So here A can be 0, Q1 is 0. So here A is 0. So how many bits are there in the multiplier? Those many zeros we have to initialize, and Q1 is also 0. So Q0 is the LSB of the multiplier. The LSB of the multiplier is 1 and the Q1 is initially 0. And the counter value can be how many number of bits in the Q. Those can be initialized here. So it can be 4. In the first step, we have to take the 2 bits and compare whether which combination it can be fall into. So here it contains Q0 is 1 and Q1 is 0. So it contains the 1 0 combination. So if it all 1 0 combination, then we have to perform A minus M. Then arithmetic shift right operation can be performed and next the count can be decremented. So in order to perform A minus M, so 2's complement addition can be used. A value is this. With this 2's complement of M is added. So this is the A value, Q0, Q1. Then you have to perform the arithmetic shift right operation. So it is a ASHR. So MSB bit can be copied into positions. Next, the shift operation has to be performed and the counter value can be decremented. Now we have to consider Q0 and Q1. It consists of the combination 1 1. If it all a 1 1 combination, direct arithmetic shift right operation can be performed and the counter can be decremented by 1. So now again the shift operation can be performed. And counter value can be decremented. Next we have to consider the Q0 and Q1 combination 0 1. In case of 0 1, the addition operation on A and M can be performed. Later on arithmetic shift right operation and counter value can be decremented by 1. So here M value can be added here. So M value is 0 1 1. This value is added here and counter value after addition you have to perform the arithmetic shift right operation. Okay, and perform the arithmetic shift right operation and counter value can be decremented. So in this way, by checking the Q0 bit as well as the Q1 bit, the 4 possible combination has to be checked and validated, and depending upon that binary, if it contains the value of 0 0 or 1 1, so the same sign can be there for the multiplier and multiplicand. At this moment the arithmetic shift right operation can be performed and counter value can be decremented by 1. And if at all it contains the 1 0, then the subtraction operation can be performed with the help of 2's complement addition, and later on the arithmetic shift right operation can be implemented. Next, in case of these two bits contains the 0 1, addition operation can be performed. Next, the arithmetic shift right operation can be implemented, counter can be decremented. So this has to be performed until the counter value can be 0. So this is the Booth's multiplication algorithm. Next, another mode of multiplication can also be possible, that is the array multiplication algorithm. In array multiplier, digital combinational circuits can be used. So, used for multiplying two binary numbers by employing an array of full adders and half adders. So, with the help of digital combinational circuit, the binary multiplication operation can be performed. So, this array is used for nearly simultaneous addition of various product terms in word. To form the various product terms, the array of AND gates is used before the adder array. So, here consider two terms B0, B1, A0, A1. So, in order to perform the multiplication, the first term can be taken into consideration, multiplied here, the two terms can be written in the partial product as A0, B0, and here A0, B1. And considering the next bit, and the terms that are written in the partial product are A1, B0, A1, B1. Next, the addition operation can be implemented. So, the last product terms are C0, C1, C2 and C3. So, we can use the digital combinational circuit for performing the multiplication. So, to perform the product terms, the AND gate can be used. And to perform addition, the circuit that can be used for implementation is the full adder or half adder. So for this example, the digital combinational circuit is, so in order to produce the first term, term is A naught B naught. So for this indicate B naught and A naught. So here the product here produced is A naught B naught. Next, A naught B1 can be given one indicate. A naught can be here B1, A naught B1. This is the product term. Next term is A1 B naught. So here this indicate will produce A1 B naught. Next term A1 B1. So this indicate can produce A1 B1. Okay. So after this, the partial product terms can be added. So in the first term, it is a single term. So this summation can lead to the product term of C naught. So directly the C naught can be coming here. Next, A naught B1, A1 B naught has to be added. So these two terms can be given to the half adder for addition purpose. So the sum can be C naught, and if at all any carry produced, that can be given as input to the next half adder. So next term has to be added here. C2, C3 terms can be produced by this array multiplication. So with the digital combinational circuit, the multiplication can be performed with the help of AND gate and half adders and full adders. So binary multiplication can be performed with the normal multiplication algorithm. In the normal multiplication algorithm, the time complexity and space complexity is more. So in order to avoid this, the Boo's multiplication algorithm has to be considered. The Boo's multiplication algorithm is efficient than the normal binary multiplication algorithm. It considers the 2's complement numbers, and the time complexity and space complexity is optimized in the Boo's multiplication algorithm. And here, to preserve the weight value, the arithmetic shift right operation can be performed in the process of multiplication. The signs can be preserved in the Boo's multiplication algorithm. So the Boo's multiplication algorithm has to be checked 2 digits Q0, Q1 depending upon the various combinations. Either it has to perform the addition or subtraction with the 2's complement or arithmetic shift right operation. So after that, the combinational, with the help of combinational circuits, the addition operation, the multiplication operation can be performed with the help of array multiplier. The array multiplier can consist of AND gates, half adder and full adder circuits to produce the binary multiplication. These are the combinational circuits which help to provide the binary multiplication or the product terms. The product terms can be in the partial product terms has to be generated with the AND gates, and can be the sum can be performed on these partial product terms with the help of half adder or the full adder. So in this video, we discussed variety of binary multiplication. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.